So I will now go into the automated testing lesson here, and I'll with me here for this lesson, I have Oskar Tobert from CSE. So hi Oskar.
Hey.
Hey. So automated testing is on the schedule, and yeah, we have already here in the icebreaker questions got all of you participants to think a little bit on what testing can be about. So perhaps if I start with you, Oskar. So what would you say are the relevant cases for using software testing?
Well, for me, I'd say it's there are, I guess, several aspects to it. First would be if I implement a new feature, I would want that to work as expected. So I make sure that it does with tests. And then I also want to make sure that I haven't broken anything that already exists. So and I test that. And I guess slightly related to the first point is sort of if you start with a test or like start thinking about how you test things, then it helps you also think about how you want to organize your code or how you want to develop the code in the first place. I think so.
Yeah, thanks. Those are all very relevant points, and I think in particular that the last thing you said is that if you have testing in mind while designing and implementing code, then that's a good mechanism to guide you when you write the code in the first place.
Mm-hmm.
Here are in the last material here are also some statements here. So a very common thing is that you do not start from scratch. You are perhaps you're downloading to try out some new code, and you find, oh, this is relevant for me, and you might then need one or two more features which are not available, and you would like them to implement it. And then it's very good if you can soon establish that, okay, this code is working, it's working on my machine, and if I now go ahead and implement a feature A and a feature B, then this will not interfere with the already existing functionality.
Mm-hmm.
So during this lesson here, we will have some demonstrations, and there will also be exercises. For the exercises, we encourage you to work primarily with Python, and within the CodeRefinery code environment, you have a tool Pytest available, and that's a framework for performing testing, working with Python code bases. There are similar type of tools available for other languages. There are also tools which are language agnostic, so they can be used then for different languages. And yeah, we will highlight a few of these during the lesson. So one aspect of testing is that maybe we're working here with software and computing. One can draw a little bit of an analog to testing in the context of measurements using physical devices. Those could be mechanical measurements, could be electronic measurements. And within scientific research, you could it's clear that if you're, for instance, in the physical sciences and you have some detectors of that could be velocities, could be positioning if you have a mechanical problem, and could be, for instance, in condensed matter physics, could be, or chemistry, it could be measurements of photon emission spectra and so forth. And it's very important there that you establish a base case and to calibrate your detectors. And where you are then in a regime where you can be on firm ground and perhaps have some reference data also. Once you have that, you can then move into using your instrument, be it a physical instrument or be it a scientific code, and then have reasonable confidence in that that your tool will do the job also in this new situation. And Oscar, what do you say? Can one arrive to, let's say, 100% confidence that things will work?
I would say no, because, well, the person who wrote the tests, they also had certain constraints. For example, they were using definitely a different, or very likely a different machine than what you're using. So they sort of all of the assurances they could make are done through a specific lens that may not sort of completely overlap with your situation.
Yeah, precisely. That's something that also relates to the concept it is known as code coverage, where one will try to make a code. Okay, in our sense, code coverage would have is how much of the code base is tested, but here also this that how much the tests will cover the functionality of a code and various use cases and various edge cases.
Yeah, but and I'd say like coverage is a useful metric, but it's not infinitely strongly correlated with the sort of safety or security or like confidence that your that all of the code works entirely as you would want it to. But yeah, it's a start.
Yeah, right. So here we have some examples here in the lesson materials with to some papers, and I think this one here, this you can check out here. A scientist's nightmare: software problem leads to 5 retractions. And that's quite interesting story. So in brief, what happened here is that some scripts were used on different operating systems, and when the original developer of the tool had been running for his or her computer, things were all working. Then the code was being used also by others, and they had other computers, other operating systems, and somewhat unexpected things happened then. So the way that the program executed was not as intended. And yeah, in this case, yeah, this had rather severe consequences because many people were using this for over many years without noticing.
Have you ever experienced something similar, or were you lucky?
No, not of that type. No, that could rather be my experience of things going wrong with I mean, in connection to testing would perhaps rather be that the functionality that was implemented in a program written by me and my colleagues, that perhaps you didn't implement what you had intended to implement. So yeah, for us working with physical models, that would simply be that they did not implement the mathematical expressions as formulated. Which is also something that can be tested. We will come very soon here to various kind of tests, and I would say here, this that I then encountered is that if you have complex numerical modeling where, I mean, naturally you do this on the computer because you cannot do it with pen and paper and by hand. Then if you can test and verify that for the very small programs, problems where your calculation is of a small problem size, you can perhaps do it with pen and paper. If you can then establish that these are correct, or things are, let's say you get it to a 0 result, or something is invariant, doesn't change over time, then you can incrementally increase the problem size, go into the real problems, and you can then build up this confidence that your code will do the job. But yet here, this is also a regime where you cannot really arrive to the like the full 100% confidence is sort of an asymptotic. Because it might be that you cannot, should say, compare things because you don't have a full reference case.
Mm-hmm.
Okay. So we can start here by example here. So we have a small snippet here of code. This is here about conversion of temperatures from the Fahrenheit to the Celsius temperature scale. As you can see here, there are multiple tabs for Python, C++, and also other languages. And this now will illustrate the use of the Pytest framework. So I'll copy this code here. You have a copy button up to the right here. And I call this source code file Fahrenheit.py. Copy and save. And then now I just run it, Pytest. So I gave no arguments here. So what happened here is that Pytest have looked here in this directory, and it has picked up here in this source code file a function definition which starts with test underscore and then Fahrenheit to Celsius. So it will then execute this function. And what you can see here is that here is defined an expected result, 37.7. This temporary variable C here is assigned from the call of this function, where you call the function with 100 degrees Fahrenheit. And here, within here, Fahrenheit to Celsius function, you have the conversion then from Fahrenheit to Celsius according to this formula. In this test function, you use an assert statement that the absolute value of the difference between the obtained result from the function call and the expected result should be less than 1 part per million. And yeah, indeed, that is what came out and executed this function. So all look good here. So yeah, so what can tests help you do? I think we already touched upon that right in the beginning of the lesson. So preserving expected functionality, you can help users to be confident that the program has been installed correctly and that it is working. You give developers, and that can be yourself or could be external people, the ability to start out from something that you know is working, and then you can add on features, and then you can check also that the new stuff are not breaking the already existing functionality. So discussion. When would you say that it's not really needed to add tests, Oscar?
Sorry, come again. I was looking at the document.
Yeah. Okay. So in what situations would you say it's not necessary to do any explicit tests?
So, well, there are also some examples given here for. So since I mostly work in machine learning, there are some things that are difficult or impossible to test. So testing an entire neural network, that's kind of difficult because it's kind of stochastic and it's a black box. So yeah, there I would say I don't bother. Then I focus more on things that I can test well. Like if I implement a new metric, for example, that then evaluates that model. But yeah, that's one thing. The things that are difficult to test. For the example, things that are sort of obviously correct, I would say it's still very often it can be good to write a test. Maybe it's not very high priority, but still it can be useful to do that. Because, well, I generally don't trust myself very much, so I think it's still useful to write the test to make sure that the code is correct, but also to make sure that you are sort of thinking correctly.
Yeah, that's a good point. And when it comes to this with so it can happen that one thinks that, okay, testing that brings a lot of overhead, and let's say that the code you're working with is 10 lines of code, but like the test stuff would be 30 lines of code. That seems like rather expensive and time-consuming thing. However, that it depends a little bit on the workflow that you get up and started with, because with Pytest, and we'll also see a program here called Catch2 for C++ code, then, I mean, you do have this machinery implemented, and you can then relatively quickly set up new tests and also to run them in a quasi-automated manner.
And what I really like Pytest in part because it does not give you much overhead. You saw earlier, you just wrote a function that did the thing, and you did not even import anything from Pytest or anything. You just wrote a code that called what you were doing, and that's it. And you made an assertion, which is also not really part of Pytest. It's just normal Python. And yeah, that's why. So I really like Pytest in that sense. So I prefer it over the other testing suites in Python, and also for most other languages where I'm aware of any.
Yeah, that indeed it is neat that it's readily available and sort of not difficult to install. So we will soon move into the first exercise. However, before doing so, we will here go through here rather briefly, but go through, I mean, the various kind of tests and testing concepts that are out there. And this nomenclature can be good to be acquainted with, because otherwise you might misunderstand what tests are actually being run for a code. So unit tests, those are tests when you test one function at a time. This can be good to work with when you are starting to write a whole program from scratch, or individual modules of a program from scratch, because then you can implement the tests one at a time, or let's say perhaps multiple tests at a time. And this Fahrenheit to Celsius code snippet is an example of that, where this small test case was, we can presume that was written right after defining the function. So you do it as you go. Integration tests are when you test how the part of the program are working together. So let's say you have like 10 big building blocks in your program. You might want to see then, do these 3 blocks, call them A, B, C, do they work together as they should with the API, that everything is matching with data types and so forth, and also then that the intended execution is proceeding as intended. End-to-end tests that would, and here certainly it depends a bit on what kind of program you're working with. But it could be that will involve, so to say, the whole code base, or that it would, in any case, do something, so to say, from the very start to the very end. And I'd say that this is something which, if you have, let's say, in scientific computing, numerical modeling, some use cases where you, let's say, you start with a set of input files, and then you crank it to the program, and you get a set of output files. That situation is something that lends itself very natural for end-to-end tests. If you, on the other hand, have something which is more, let's say, event-driven or user interaction type of program, then it could be perhaps much more challenging actually to set up end-to-end tests that are representative for how the program is used. Regression tests are something that relates a bit to end-to-end tests. So what is rather common is that you set up some reference cases where you are then confident that, okay, the program did for given input produce the right results. And perhaps the confidence in these right results are both in that the program was, written in a correct manner, but also that you compare with, let's say, completely other programs that are perhaps implementing similar functionality. So that could be, so to say, perhaps among your colleagues or the science community, could be also from your, let's say, rival researcher group that are trying to do similar stuff also. So these were a few of them. And then we have test-driven development. And Oscar, what can that be about?
So, well, normally you maybe just start thinking about your fantabulous new software that you want to write, and maybe don't think as much about how all of that what you're writing is actually being used. And test-driven development is one way where you can try and sort of invert that, where you first think about how it's used, because you first write the test that uses the software that you're about to write. And yeah, then sort of continue developing that and continue testing it until the test passes. Yeah, that can be a useful approach for some problems. It's certainly not a universal solution to all problems, but yeah, it can be an interesting approach to have a different sort of viewpoint on how to make software.
Yeah. That's yeah, indeed, and sometimes and if some of you in the audience here, perhaps you're working at private companies, and what can often seen is comparing a little bit the situation in academia and in corporate settings. You often have you have larger teams in companies, and test-driven development is sometimes, I know it from own experience, where we have in a unit or department where you have some engineers who are really, for instance, they write the specifications for some program, and then they also write tests. And these people themselves will perhaps not then work with the code base, but that will then be done by other members of the team. So this is, it's clear here. If you want to do all of these various things, all kind of different tests, it helps if you are a large team.
But I guess usually in a scientific, well, maybe it depends a little bit more on the context, but as a PhD student, for example, then you are probably mostly writing or like working on your own and then you are the same person who writes the test will also write the code itself, oftentimes.
Yeah, indeed. Great. So continuous integration, code coverage, we will come to that a bit later, and we'll define what these are then. So I think now, also in the interest of time, that we will move now into what will be the first exercise for today. So we go here to the next section of the lesson here. So what you will do here is that you will get some hands-on practice on testing some functions locally. And testing locally is, I would say, that's sort of the base case where you can do everything on your local computer. Then in, so to say, real life, you will often then do testing on various services such as GitHub and GitLab. So we will just very briefly introduce the exercise, and perhaps has some posted it into the shared document. Yes, I see the link is here. And there are two tests here, testing local 1 and local 2. And then the suggestion is that you can get started with this minimal example, local 1. And some of you might be able to do it rather swiftly, and then you can move on to the other example. So the instructions can be found here in the lesson material, and you will be using Pytest, and you will work both with a code that will pass the test and with tests that, with code that break the tests. So are there any more instructions that you would like to give, Oscar? Or
well, yeah. So you implement the function, implement the test for the function. The function is adding two numbers together or two anythings to two Python objects, and yeah, then test it. Not much more to it, I think. And then for the other one, what's important is that you are now so the function is the same. You're adding a new test for what happens if you try and add floating point numbers. There might be some like special considerations, but yeah.
Yes, indeed, that adds some extra complications to it that one will need to deal with. So with that, you are then welcome to start up the exercise, and it's now 34 past the full hour, so we will reconvene here at 54 past the full hour. Bye for now. Welcome back, everyone. So we hope that you have now been able to work through the first exercise and perhaps also the second one. So there are a few questions that were posted in the collaborative document, and we would like to highlight some of them. And yeah, first one here is how to avoid that the execution of the tests will not interrupt. And so a good practice is to put each assert in its own test function. I think this might depend also a bit on which testing framework that you're using. That might also, so to say, be language specific. So second question here is about testing in for machine learning, deep learning models. So yeah. Okay, one thing to learn from this discussion here, the question and answer, is that for something like a big deep learning model that can take a long time to train, you might want to do the testing for, so to say, smaller cases, and it might be that it's just too expensive if you need to run the full training and then validation with test data.
I would also say
yeah.
It's not just a problem of expense, but also the model sort of it's a statistical problem usually, and so, or it's you don't have, like, it's often not sort of deterministic in the sense that when you train a model twice, it will not give you the exact same answer probably. And so that is then difficult to check, even more difficult. Well, you've done the exercise now for your floating point numbers. It's even more difficult than for those, for the floating point numbers. Because if you have a language model, comparing two sentences that it produced can be tricky.
Yeah.
At least in the context of testing.
Yes, indeed. Yeah, and the question number 5 here, how the testing works, and the key here is that you need to check up on what are, let's say, the keyword constructs in the respective framework. So for Pytest, it's test underscore, and sometimes you need to use some other construct or to register the tests with macros. So yeah, you simply need to follow that syntax, and we will see a bit later here one example of how that is done with catch2 for C++ code snippet. So we will now proceed to talk a bit about automated testing. So the outset here is that we would like to explore how we could implement automated testing that will run on, for instance, on each time that we push changes to a repository. And yeah, here's a little bit of question that we can keep in mind. So why is it good to auto-close issues with commit messages? And yeah, you will see that in a minute. So this part now will be run as a demonstration, and we will then make use of the so-called GitHub actions. There's also the GitLab continuous integration framework. And in addition to these services, there are multiple of these around. So what I will do now is that I will set up a new Git repository with some starting code in, and I will configure tests to be run as a GitHub action. We will see that this code will contain some bugs. We will not notice that at first, but when we start to run, let's say, all parts of the code, we'll see that, oh, here's something which is not working, and that will then be caught by the tests being run on GitHub. What one then can do is, and this is also very important in the context of collaborative code development, is that, I mean, you make a note of it so that you don't forget it. And one inbuilt functionality to do that here is to use the GitHub issues functionality. So report a bug as an issue. Then someone, and that can be yourself or could be one of your colleagues, can spot this issue and work out then, okay, how can I fix this? And then go ahead and fix it, and then contribute this fix in a feature branch, and you push it to the GitHub repo. And as you will see then, if I set up this automated testing machinery as a GitHub action, then the tests will be run directly after pushing, so that this, so to say, the code fix will then be tested to see whether it actually then have resolved the bug. And if that is affirmative, then one can then go ahead and merge in this new code, and you have then, so to say, improve the program by correcting the bug. So let's get started. So I will go to my GitHub, and I will, now I have already a copy of this, but I'll create another example here, another repo. So I call this repo example-ci for continuous integration. It's a public repo. And yeah, I just go with the defaults. And here is, yeah, the SSH URL for cloning it. So I copy the URL. Then I go here and I clone it. And here in the terminal window, it reports an, oh, you have cloned a empty repository. But that's perfectly fine. So I cd into the directory. Does only include the .git directory. So here are the code snippets that we'll work with, and these are in Python. So in this file, functions.py, we have some simple arithmetic functions. So I create this source code file, functions.py, paste the code, save it. Then we will have another code snippet, test_functions. And here is where we have then the definition of the tests. So I'll put that in another source code file, test_functions, py. I paste it and save it. And as you can see here, this red block here is Python code which has been commented out, and that we will activate later. And let's see, the Git status is that we have 2 new files here which are untracked so far. We will add them. Git add functions, git add test functions. I call these added functions and tests. Commit and push. So, okay, now I already contributed this to the instance of the Git repo on GitHub. We could also then, independent of this one can test the code locally. So Pytest see what it finds. Yeah, okay, it goes into the test.function source code file, picks up these test definitions and execute them. So one test was executed and that one test passed. So now we will enable automated testing. So I will now go, as you can see here, there are tabs here for how to do that on various platforms. So also for GitLab and for and for GitHub and for R. The most straightforward thing is to use the GUI. So what I'll do when I go to my GitHub page is to click this Python applications button. So I'll do that. Go to actions. Scroll down a bit and then press the configure button. Now there are a few things here that, as you can see here, what is coming up here as a template is this within the .github and workflows directory is then templated here a YAML file python-app. In the lesson material, we have some stuff that we would like to add in here. So I will copy in those lines of code from, I do it from another window, not shown here on the stream. So I will here for these permissions here, have contents read, and I add a line here, pull request write. So what this YAML file is about is that it's in a with this YAML format, it is a specification on what actions that are to be run automatically. Another thing we need to add is we would like to augment here. So after this pip install flake 8 Pytest, we'll also then add Pytest -coverage -cow. And
I think there was earlier a question about how to measure coverage, and this is a way to do it sort of automatically. There's existing tools, and you don't need to worry about that yourself.
Yes, that's right. So there are these tools that can do it for you. But obviously, it's also good if you bring in also your own insights into what things are the most important to test. Because I think the coverage testing here is simply keeping track of how which lines of code are being touched while executing the tests. So it's sort of a metric which is it's simply telling you in terms of lines of code where you have been traversed while using the running the test, but doesn't say anything about how, let us say, central are these part of the code for the functionality of the program. Okay, then I add here at the end this coverage report thingy. And yes, I think we are done with that. Now in order to see the commit button here, I need to just increase the size temporarily here. Now you don't see it on stream, but I commit the changes with the default commit message, and I commit directly to the main branch. So I now resized the window pack. And yeah, so what we see now is that in the last commit message is that we created this python-app YAML file. And here, there's a little status symbol here, which says that the tests are, or some action is pending. It's here in this like red brownish color. And if we rephrase, reload the page, let's see what happens. Okay. So here we have a green little hook here, and yeah, it tells us success here. So that's a good thing. This was step 4 here in the lesson material. Verify that the tests have automatically been run. So now we will start with so now we have the base set up here, and this last thing we did it on the GitHub instance of the Git repository. So we don't have it locally yet. So I go to my terminal and I type git pull. So now, yeah, this python-app.yaml file was then pulled in here. So now we have it here also. So we will now look into this test_functions file. So we already had, so here, yeah, I removed the Python highlighting here to have more clear colors on the screen. There is here definitions for the tests. So now for start, we remove the comments here, so that you have a test definition also to test subtraction. We save this, and git status. Yeah, we have changed this file. We add it, and then write in the commit message, added test of subtraction. Save, push. Then let's go to the GitHub page. Reload. So latest commit, added test of subtraction. It's pending. And yeah, this one should be fast, but yeah, okay, now it's wrong. And now you can see there's a red X here. So press that one, and yeah, all tests have failed. Click details, and here you can see. So we have, yeah, the assertion was that the test would yield that we would return -1. However, we obtained 5. So it was therefore not fulfilled. Okay. We could have obtained that also locally with Pytest, but now we did it here on GitHub. So go back here to the main page for the repo on GitHub, and then go to issues. I create a new issue and write then subtraction is not working properly. And then I create it. Okay, so in this case, I think I already spotted in the code where it goes wrong, but let's presume now that I'm stuck here. I need help from someone, and I've spotted the error, and I reported it as an issue. And now, yeah, my colleague Oscar will see what he could do about it.
Yeah, Jano, could you switch to my screen? Thank you. Well, that's not quite right, I think. Yeah, there you go. So I just I forked the repository. I guess I should sync it. I'm probably a little bit behind because I did it earlier. So let's do that. And here we go. And then I also cloned it already. So okay, so now I have everything locally that that Johan has. Let's run the tests again locally. Of course, one should of course do that as well. Let's check now again. Oh yeah, so we see tests have failed. Why might that be? And I can look at the test. So so I can see the test makes sense. 2 minus 3 should indeed be -1. Then look at the code that is being run, maybe. Subtract. So, this is I plus 2. That is, I found the mistake. So I've made a change. So let's run the test again. And now it passes. Hooray. Then let's add our change and commit. Now, what should I write as a commit message here?
Just a moment here. So now, which branch are you in for the moment?
So I'm, I believe, still in the main branch.
Yeah.
But I am, yeah, I guess I could have made a branch for that fix, but I am on my own fork. So I'm not on.
Yes. Yeah.
Johan's.
Yeah. Right. Yes.
So I could not directly commit to Johan's direct repository, but since it's my own copy of it, I can. Yeah. So, well, I'm about to do that, but first I would need to commit my changes. So, yeah, fixed subtraction, I guess. Should I write something about that I fixed an issue, or should I put that in the pull request message?
So, I mean, here you tested it locally and you saw that it worked. So then I'd say, you could go ahead now and write then with the, yeah, with the square symbol, fixes, and then number 1, because it was issue number 1.
Okay, the most important one.
Mm.
All right.
Yeah. So these fixes or closes or close, and then followed by the number of the issue, will do some magic then on GitHub.
So let's switch back to GitHub, and we can see here when I cloned when I forked the repository, it also copied, for example, all of those GitHub actions. So you don't need to reset them just because you forked something. They come with your fork.
Yeah, because that YAML file is included in the Git repo.
Yeah, and so you can also see the nice thing is, well, I wouldn't have had to remember to locally test anything. If I push it, it gets tested automatically. You don't need to, you set it once and then you kind of forget about it, because then whenever a test fails, you'll probably get an email from GitHub.
Yes, yeah, you're right. Yeah.
So see, we can see success. Tests have completed. Yeah, seems to look fine. And now I, of course, want to make a pull request to contribute back to that, to the original repository. Where is that? Do I have to be taller? Contribute maybe. Open pull request. Sorry, you probably don't see that. Let's come back. I guess this, yeah, we will just use the commit message as the title. I don't think we need anything further. And then, yeah, we create the pull request. And yeah, let's switch back to Johan's screen.
So we now see the repo on my GitHub, and I'll press refresh. And okay, it didn't show up like that, but with a color bar. But I can see here, yeah, issues. We have one still. Then here, pull requests 1. I click here, and yeah, then I'll see it. Fix subtraction fixes error number 1 or issue number 1. And
maybe old, but I say pound once.
Yeah. Okay. Approve the workflows to run. Click this. So they actually, you see here, there are a few tests being run here. So what's running here, that's the Pytest stuff that we had set up with the actions. Then here, oh,
what happened there?
What happened there? Okay. Okay. Well, if you look on this part here, so the test case for addition and subtraction, each of these passed. So that's passes. That thing is fine. But now here's for the coverage thing, which something is not working here. Then I don't know what we are missing. Yeah, if you spot something, you're very welcome to write in the shared document.
But so the coverage report, well, at least there are no conflicts. That's good news.
Yeah, perhaps there was some typo when I edited in the YAML file. I actually think that I think right now is not the time to arrow check for where it goes wrong, but I would presume it was in the YAML file. But we can observe here that we have no conflicts with the base branch, and therefore I feel, so to say, happy to merge this. Confirm the merge, and then the code is merged. And now refreshing here, we can see that both the issue and the pull requests are, I mean, we don't have any open on these. And I actually say, what happened now? Okay, we don't know specifically what went wrong here with the coverage thingy, but I say that something like this is happening not so seldom, I would say. In the sense, you have the testing in place, but you don't have clean termination of everything. And yeah, I do think, of course, if you have clean termination of all the tests, but if something happens like this here, then yeah, perhaps you could nevertheless go ahead and merge, as long as you know what you're doing. And then you might then get back to it in the next day. Great. We will have a break shortly, and perhaps then we could revisit what happened and get back to you on that point later. But now it's high time that we will have the break, and so let's see how much time.
I think originally it was 10 minutes.
Yes, so let's go for that. It's now 28 past the full hour, so then let's reconvene at 38 after the full hour. Welcome back after the break. So right before we went into the break, we noticed that this automated test for my Git repo that it failed. Turned out that just refreshing the web page and to look on the test being run then after the merge of the code, then everything was smooth. So what might have happened is simply that it failed on this particular instance when it ran the tests at first, and yeah, it can be good to be aware of that this can happen. So with that, I think we can conclude the part on automated testing, and we will now move into test design. So Oscar, please go ahead.
Yeah. So this comes also with an exercise that's which you will also spend at least, well, say 20 minutes with. It's mostly about different types, like different scenarios. There are different kinds of functions and classes, or in general code that you might want to test. We have in total 10 different scenarios that you can look at. The first 5 or so are sort of on the simpler side, and the later ones are a bit more complex. So I would recommend during the exercise that you start with a simple one and then maybe go into the more complex ones when you've done a simpler one. Yeah, so there are, I won't maybe go through all of the ones, but yeah, so the first one is just simple: number comes in, number goes out, with a mathematical function essentially. Then the second one would be like on strings and a number. So for example, counting words. Then you have files. So files are always interesting. Then we have, I believe, random. Oh no, this is external dependency. So this is for something when you imagine the code that you're writing interfaces with some kind of hardware, for example, a sensor that is not present necessarily while you're testing. So you'd have to find some way around still testing your software or your code, even when that hardware is not present. Then you have something mutable, so sort of you can have side effects, and you have to make sure everything still works as expected. Then yeah, and then the more complex ones start. I won't go through all of them, but there's also some random numbers and some more interesting things to explore. And yeah, if you have any questions, then just reach out in the collaborative document. And I'd say then, yeah, start with the exercises. You have 20 minutes from now. And yeah, so it's 42 past the full hour now. So we'll see you 2 past the next full hour. Yeah, have fun. Bye. Yeah, welcome back. So yeah, there were 2 questions. I think we'll get to them. For the second one, generally, well, there's the testing frameworks provide facilities for that usually, but you can, in Python at least, also just handle the exception that you're expecting and not any of the other ones. That would at least should achieve that what you're looking for. But yeah, let's go on since we're already quite late. So next would be we'll maybe go back. So because for now, or until now, we've mostly talked about Python and Pytest. And we promised that we would also at least take a brief look at some other frameworks. So yeah, let's look at C++, and we'll be using Catch 2. So yeah, we're going back to this example where we're trying to add 2 numbers. And yeah, let's look at how that would go. Right. So I have this minimal example. The example is, yeah, you can, I won't type it out again, but so we need to include these macros that Catch2 provides, like so. Then there is this here is the actual function that we're implementing. So it takes a number, and a number could be yeah, different things. And then yeah, the function name, and we add them together like so. And after that comes our test case. So we have these well, here the integer test. Maybe Johan, you can maybe explain what does this add in square brackets? What does that do?
Yes, I think yeah, good question. I don't know if it's a label or if it's a keyword here.
Oh, okay.
Yeah, so add is also the name of the function that we have defined.
Mm-hmm.
And
Okay.
then here in the test case, we have the int test. I mean, that's int for integer.
Yeah. Yeah, but so test case in any case is a macro that is provided by this include statement, and this requires also comes out of that include, and yeah, so whatever's in there is just a sort of parameter to this macro. And in this require, we then call our function with some parameters, and it works very similar to this assert that you saw earlier in Pytest. So that's our code. And then Catch2 is very integrated with CMake. So we're not sure how familiar you are with CMake. I'm not very familiar with it. I tend to avoid those kinds of things, and in Python you don't really need them usually. But yeah, so CMake is in the broadest terms, I guess we could call it a build system. So you can use it especially for compiled languages to build and sort of build the binaries, or well, it's a bit more powerful than that, but you can sort of use it to take your code and generate something from it. And in our case, so most of the time that's just compiling it to the binaries that you can then execute, but you can also use it when you're in conjunction with catch2 to run tests, for example. And so this is how our CMake lists file would look like. So this is the description of the project and what is supposed to happen when you how you build it, in whatever that means. So first is some sort of preamble, and then what we're doing here is we tell CMake to download catch2, and so you don't need to sort of install it yourself first, which I have also done, but it's not sort of strictly necessary, because you can sort of put that in there and then CMake will do that for you. Then we do, so this part down here, that is also basically provided, or sort of catch2 understands this. So enable testing, then we add an executable, which, so this is example here. It will also tell that to compile that executable. And then example CPP is the source code for that executable. And then you have to link the libraries from catch2 that you would need to run the tests, and sort of do all of the things that the testing that, for example, in the other scenario, or in the other for the other language, Pytest would do. And then we would need it to catch2 how it finds the test that we're running. So now, how does one actually run that? So you can see in the description here, you run the test. That's a little bit more complicated again. In Python, you just run Pytest. For catch2, you would need to run this. So, and again, I'm not too familiar with CMake, so this will kind of prepare all of the stuff that is just there for the testing itself. And now, in order to compile the actual executable binaries, like so, and that takes already, I think, unbearably long.
Why is that? Why does it take long time here? Because our code is very short.
Yeah, well, I would suspect that our code is very short, but the catch2 test, the catch2 code, and is not very short. It can do probably a lot more than we are currently asking of it, and I guess it's relatively complex.
Yeah, exactly. No, so indeed. So here, as defined in this CMake list.txt, we are fetching the catch2 framework, which then is now also built together with our specific application code. This is one workflow. One could also have, you could have a standalone installation of catch2 on your computer, and then instead of building it each time, you could then link to it and have also include statements while you are building your specific code.
Okay, so if I did it again, does it cache it?
Yeah, well, if you would add it here, let's say that example.cc source code file here, but everything else, including the fetched code for the catch2, then CMake will then figure out that it will need to recompile only the source code file that you have changed. So in that regard, it is catched. But still, this is just local fetched code to be used within this directory here.
Okay, yeah. So you can see I just made a trivial change that is significantly faster.
Yeah.
Okay, yeah. So we've built everything now. So and we built it into the build directory. So now we run it, and I believe that is the ctest command, and you can see that also goes relatively quickly. And yeah, our one test passed. Hooray. Yeah, so since we're already quite late, we had a more complex example for that as well, but I would suggest that we skip that and move on to our next point in the agenda, which is maybe some conclusions. Yeah. What would you say? What's the main takeaway, Johan?
So yeah, one main takeaway is that I mean, testing is good and it's important. Often there's a bit of a learning curve for these tools. So Pytest, which are mainly used here, is rather smooth to get started with. For compile languages, yeah, certainly it can be a bit more involved. So it's a little bit a question of mindset here, that you simply need to, I mean, need to figure out for yourself whether, let's say, is the code that I'm working here now, is it something, let's say, something major, something that I and colleagues will use over many months of time or even years? Yes, if that's so, then it's worth the effort to get going with testing. Automated testing really helps, because that enables you to have the tests being run without you having to monitor it automatically. There's a large convenience factor here.
Yeah, I would also point out there, so we used mostly Pytest, and for the most part, it was kind of almost invisible. The only thing that, or depending on how you solved the exercise or how you approach them, you maybe only used Pytest by calling Pytest. But there are also additional features that you can use inside of the tests while you're writing them. For example, when you are testing floating point numbers, then you can use Pytests. It offers some facilities to set the tolerance, which might be sort of a little bit more robust than sort of just checking sort of the absolute difference between the output and what you were expecting. And it offers some more of those things. And one thing you might want to look at that we didn't discuss are fixtures. Yeah, so there's a little bit more to Pytest than we showed. But yeah, I think the nice thing about Pytest is that it provides a relatively smooth on-ramp, very much unlike something like Catch 2. Yeah, I was mostly exposed to it in preparation for this lesson today, and yeah, I would say I'm not very sort of comfortable with it yet. I would need to spend a lot more time to actually understand everything that's going on there. Yeah, but yeah, and I would say I use Pytest quite a lot, and I would yeah, recommend find a framework that you like and learn it. Yeah.
And as we touched upon earlier also, so I mean, your code is one thing that you need to, I mean, as a developer of code, you naturally have a responsibility for its functionality, but then there's always an environment in form of, I mean, running on different computers and running on different operating systems. And there, a common thing is that you then, I mean, you need to be ready to work with the available resources, and I mean, things can happen. So just because the program is working perfectly fine on your personal computer doesn't necessarily imply that a code might flawlessly work on some other system. So I mean, in particular for codes which are rather where you have worked through all of, let's say, the more obvious bugs or things that just go wrong while developing it, then it's important to be aware of that unexpected things could happen if the environment changes. Let's say you upgrade your operating system, or if you run on another computer.
Yeah.
And it's clear that for some of these, without having a testing framework available, it would be rather challenging to actually to test these things, because if you have like a large program, you cannot, let's say, devote the time to try things out just on your own and by optical inspection, because that would be much too time consuming. So if you then have a test suite delivered with a program, then yeah, it's a good habit to just start that thing up as soon as you are or installing or building a program.
I would also not underestimate the kind of documentation effect testing has. It's can be really useful to see tests, and I guess at some point you'll publish software, or you're writing the software for the most part, not because only you are using it, but eventually someone else will also be using it. And that other person then needs to some extent understand what's happening. And tests can be very useful for that. And also, I'm pretty sure that is happening because, or that's going to happen because future you is not the same person as you, of course. And yeah, so future you will be then grateful that you've written tests in the past.
And here one can naturally reduce efforts that you devote to your project, so that material which go into tests can also be used like examples, and examples then also is part of the documentation of a code.
Yeah,
and that's actually very much how some large projects are working. So if you look under the hood in the source code, you will see that, okay, sometimes just like a directory which is called like examples, and then there's a directory called tests. But it could also be that it's sort of intermixed. So you have the set of examples, and you can also have the scripts that can run these example files, and then you compare, if it's an end-to-end test or regression test, that you compare the output that you get with the expected reference output. Yeah, it just strikes me here now that one main reason why you then, after all, perhaps let's say split, if it comes to, let's say, end-to-end testing, why you have, let's say, distinct set of input files for tests and for examples is that yeah, there's a practical aspect of computation time. So when you have examples, for a code, you would like to have, let's say, some basic cases, but then also it's nice if you can have some, let's say, more real use cases, and those might be then of a size so that it takes time to execute them. And this then in contrast with a test suite, the test cases that you have here should ideally be possible to run them rather quickly. And that's in particular important if you set it up in an automated workflow, so that the test suite is run for each pull request or each push to a repo.
Mm-hmm.
And clearly here one can also do it a little bit in, so to say. I mean, you can do it in different sizes. So you can work with, let's say, the small test suite, and then let's say the large test suite, and then you can run the big thing. I mean, not on a daily basis, but perhaps let's say once every week or so.
Yeah, that's a good point. That's another feature that these test suites also have, that you can filter for tests. And this way you can sort of select, maybe not test everything at once. Sometimes you only want to run a single test, or in other situations you want to run a certain subset of tests. And these test suites sort of usually provide some kind of tools to do just that. Yeah.
Yeah.
And maybe some more words, just if you are not testing currently, how to get started. So I'd say, well, since, yeah, you probably have an end-to-end test that you can sort of do relatively quickly just from the documentation or something that you've already written. And then the next easiest tests are unit tests for small units of code that are in there, sort of, if you have structured your code a little bit. And if you haven't, then that would be kind of the maybe a good sort of inspiration on how to structure your code. Yeah.
Okay,
Do you have
great.
anything to add, or give over to Samantha?
No, I think we have covered the essentials now, and I'm looking here on the collaborative document, and I see, yeah, for the time being, no further questions. Then, as usual, we have the feedback block is here at the end of the document, and I think we can now conclude this lesson and leave the word to Samantha, who will tell us about the program for next week on modular code development.
Yes, thank you both for this session. So we hope that you could take something from today's session to your own workflow and maybe learn something new. Please give us feedback. It's in the very bottom of the notes document. Something about the speed, the level of the session today, if you think that you will use what you have learned today. And if you have anything, one good thing about today and one thing that we should look into improving for the next time we are having these workshops. We're currently running these twice a year, so there will be definitely options for us to update either materials or the way we run this workshop. So please let us know. And you can also still ask questions in the very bottom of the document, or I also put the link, or we also put the link to our Zulip chat, which is the place where the CodeRefinery community hangs out and discusses, well, all kinds of topics. Also, like the organization of the workshop happens there. So if you are curious on joining us, for example, or just if you have any further questions regarding the materials of this workshop, you can join us there. We have a help channel, and you can discuss and ask more there. Then thank you also to Jarno for the streaming today. All the helpers behind the scenes, I think Richard and Michaela have been active in the collaborative notes. And of course to you for asking all the questions that you had via our document. Next week we'll meet same time, same place for modular code development lesson. And this lesson is really there to tie it all together. So we will revisit most of the topics of this whole workshop series, as it was this time, and apply them to an example. Currently, if you look from the schedule at the materials, it's all in Python. We are working on adding the same examples also for R. So, and also don't worry if those are not your languages. I think that even by following and looking how it works in Python or R, you can get also something if you are, for example, coding in Julia or so. So it's more about the topic than the language itself. And yes, And if you have any other feedback about the whole workshop or anything that happened in these sessions, we're also very happy to hear about that. Thank you so much also to our instructors. Well done. And I don't know, do we have any last last things to say for today?
Yeah, well, I could perhaps just say that, so as you might have noticed, for this testing lesson, it's rather extensive. So just a lot of material in there that we didn't have time to address. In particular, there are, I mean, the different examples in various languages. So if you're interested in these, we very much encourage you to go and have a look on these. And then there are template solutions for many of these in many of the languages.
All right, then we'll give you the last 2 minutes until past for filling in the feedback and preparing for whatever next meetings or courses you'll have, and wish you good rest of the day and the week, and see you next week. Bye bye.